After more than 28,000 engine failures, GM figured out a solution, switching to a thicker motor oil. Oh boy, there is a lot to talk about. First, why are so many GM V8 engines failing? Second, how is simply changing oil viscosities a solution? Third, the big question, are thinner oils damaging engines? And finally, should you consider switching to a thicker oil? And we'll be looking at tons of actual data and testing so that we can reach a very sound conclusion. But first, a little humble pie for the folks at GM. According to NHTSA, nearly 600,000 vehicles have been recalled after GM's fourth investigation into the matter. That is to say, their investigations are about as reliable as their engines. GM found 28,102 complaints or incidents of failure of their L87 engine due to crankshaft, connecting rod, or engine bearing failure, which resulted in 14,332 vehicles completely losing propulsion. If you're curious which GM vehicles use this 6.2-liter V8, the L87, and thus are affected by this recall, I will put up a list on the screen. But this is a huge failure rate. So what's to blame? Well, there are two primary root causes. First, rod bearing damage from sediment on connecting rods and crankshaft oil galleries, and second, out of specification crankshaft dimensions and surface finish. Okay, so somewhere in the manufacturing process, the interaction between the connecting rod and the crankshaft has gone south. This leads to these bearings getting chewed up and eventually the engines fail. So ultimately, the manufacturing seems to be the culprit here. But when I was researching this, something very comical came up. You see, one of the vehicles affected is the Chevy Silverado 1500. I wanted to learn more about the 6.2-liter V8 engine specs, so I go to the Chevy website, only to learn the Chevy Silverado is, quote, America's most dependable full-size pickup. Okay, now this JD Power data, is based on the 2022 Chevy Silverado, which, yes, is a part of this massive recall. This is a vehicle that has an abysmal reliability ranking from Consumer Reports. It's ranked 7th in reliability among 2022 pickups from them, has a 1 out of 5, the worst ranking you can get for powertrain reliability, and it's had 5 recalls. Now, I haven't seen all of the data, but I'm just saying there is a chance that perhaps JD Power should win the least dependability award. Thirsty to learn more, I dug deeper, where JD Power readily admits, quote, JD Power awards and performance ranking are based on numerical scores and not necessarily on statistical significance. Not necessarily on statistical significance. What are we doing here? Now, to JD Power's credit, the 2022 Ram 1500 has had 13 recalls, and the 2022 Ford F-150 has had 16 recalls. So maybe there just aren't any dependable American pickups. Okay, but we've gotten distracted. So we know why these engines were failing, but what's the solution? And what does this have to do with thicker oils? Well, basically, there are two options offered as a solution: swap the engine or swap the oil. Okay, so what triggers an engine replacement? Some vehicle identification numbers, VINs, have already been identified as needing an engine replacement. If they haven't already been identified, then they need to be inspected, at which point the dealers are checking to see that the crankshaft and camshaft are properly synchronized. If these are out of sync, it indicates the engine has a problem, and so it needs to be replaced. So if GM says so based on the VIN, or if the engine fails inspection, replace the engine. But what if it passes the inspection? In this case, the service bulletin calls for switching from a 0W20 oil to a 0W40 oil, a significantly higher viscosity oil. This leads to our second big question. How does changing the oil viscosity solve the problem? Now, it certainly sounds like a band-aid solution, whereas replacing the engine is a true fix. But there is some logic here. So to understand this, we need to understand the Stribeck curve. This is useful for understanding friction, where you have a lubricant between moving parts. Okay, so looking at this curve, we have our frictional coefficient on the y-axis and the Hersey number on the x-axis. We'll get into what that all means, but initially, you'll probably notice 3 distinct regions on this curve. First, we have the boundary lubrication region. This is where you basically just have straight up metal on metal contact. If you look at it on the molecular level, the two engine parts are coming into contact with one another, and as you can imagine, this creates a lot of friction and wear. If a crankshaft and connecting rod frequently operate in this region, you're in trouble. The next region is called mixed lubrication. Here, you have some separation between the metal parts with a film of oil, but it's not perfect, and some contact between metal parts still occurs. As you reduce the amount of metal contact, friction continues to decrease. Finally, you get to the hydrodynamic region where lubricating between metal parts is completely separated by an oil layer. This is where you want your connecting rod and crankshaft to be operating. Okay, so now it's time to understand the x-axis number, the Hersey number, which comes down to the sliding speed between your two moving parts multiplied by the lubricant's viscosity divided by the load pressure. Okay, so for sliding speed, this goes up as your engine speed increases, right? So the crankshaft speed relative to the connecting rod bearings gets faster. So if your engine is spinning faster, it pushes your position on this curve to the right, keeping you in that hydrodynamic region. For lubricant viscosity, the thicker the oil, the greater the Hersey number. So again, as the oil gets thicker, it pushes your position on this curve to the right. And finally, we have the load pressure. So if you're at low throttle or not demanding much from the engine, the pressure on that connecting rod bearing goes down. This means the Hersey number goes up, meaning you push your position on this curve once again to the right. So now we can understand why changing your oil's viscosity can offer a potential solution, right? Because if we have an improperly machined part that doesn't have the right surface finish, then it might be operating more often in the boundary and mixed lubrication regions of this curve. So what are the possible ways we can push the position on this curve to the right so that we don't have metal on metal contact? Making the engine spin faster can do this, but it still needs to be able to operate at lower RPM, so that's not an option. You could decrease the engine's power output, reducing the load, which pushes this to the right, but then customers would be upset that they're not getting the power they paid for. So the only other option is the oil. If you make it thicker, it pushes you to the right, potentially getting you out of the regions where metal on metal contact is more common. At the very least, it should reduce the amount of time and the severity for which you're operating in these regions. Now, you might then rightfully ask, well, why not use thick oils in all engines? We're going to get into this, but looking at the Stribeck curve again, look what happens as your oil gets thicker and thicker, and you continue to push the position to the right. Well, friction continues to climb, and yet you're offering no wear benefit. There's no metal on metal contact where you're operating here or operating here. But if you operate further to the right on this curve, you generate more friction, which means more heat, less efficiency, and this translates to worse fuel economy and less power. So that is the power of thinner oils. If you have hydrodynamic separation of your metal parts, you can reduce the friction within your system without impacting reliability by bringing your position on the curve closer to ideal. But how thin is too thin? This of course leads us to our third question, the big one. Are thinner oils damaging your engine? I want to start off by explaining what is risky and what is less risky when it comes to deciding to ignore what the manufacturer tells you should use in your car. Today's cars use multi-grade oil, meaning the oil has a viscosity grade when it is cold, in this case 5, and a viscosity grade when it is hot, in this case 30. Say your car recommends a 5W30 oil. Generally speaking, it is a bad idea to increase the first number, so going from a 5W30 to a 10W30, and generally speaking, it's also a bad idea to decrease the second number, so going from a 5W30 to a 5W20. That's because you're introducing a new region of oil viscosities to your engine. A diagram helps make this perfectly clear. Let's look at a diagram of a 5W30 oil and plot viscosity versus temperature. As you can see, as the oil temperature increases, the viscosity of the oil drops. Now, if we plot a 10W30 against this, we can see that the 10W30 is thicker when cold. So this is introducing a viscosity region to the engine that it has never seen before, and it might not be designed to operate well within this region. This could negatively impact oil flow on cold starts. Additionally, if we plot a 5W20 oil, so decreasing that second number, we can see that at high temperatures, this drops below the 5W30 oil, again introducing a region to the engine that it has never experienced before. This might be too low of a viscosity for the loads the engine provides, which could increase wear. So for both cases, if your engine recommends 5W30, you don't want to increase the first number or decrease the second number. Okay, but what about the opposite, like what GM is recommending? Say you're going from a 5W30 to a 0W30, so decreasing that first number, or from a 5W30 to a 5W40, so increasing that second number. Well, overall, this is less risky because you're not introducing the engine to a viscosity region it has never seen before. Let's look at a plot to better understand. As you can see, going from a 5W30 to a 0W30, the entirety of the 0W30's operating range within this given temperature range falls within the range of the 5W30. The engine is going to operate with the oil at these viscosities one way or the other. Same with increasing the second number. Going from a 5W30 to a 5W40, the entire range of the 5W40 falls within the range of the 5W30. So the engine isn't going to see anything it hasn't seen before. Another way of thinking about this, if you put 5W40 in an engine that recommends 5W30, it's like running that engine with 5W30, but the oil is at a cooler temperature. Because as we've seen, viscosity is highly dependent on temperature. So this helps explain why some cars will recommend using a thicker oil for track days. On a track, you're going to have consistently high loads, and your engine is going to reach higher temperatures. Both high loads and high oil temperatures push you to the left on the Stribeck curve, because high temperatures reduce oil viscosity. So by using a thicker oil on track, you can push yourself back into the happy region of the Stribeck curve. Alright, so that's important background, but just because it's less risky to decrease the cold rating or to increase the hot rating doesn't necessarily mean it's a good idea. Here's two reasons why. First, let's take the example of decreasing the first number. Say we go from a 10W30 to a 0W30. It sounds harmless, right? Well, in reality, a 0W30 oil is going to require a thinner base oil and then use viscosity modifiers to get to that 30 hot viscosity rating. So a 0 is further away from a 10 to 30, and so because of that, this oil is going to have to use more viscosity modifiers in order to reach that target of 30 at hot temperatures versus a 10W30. So these viscosity modifiers are molecules that expand as they heat up, which makes the oil thicker. But then as they get really big, they can get chopped up by the engine. So if you have all of these molecules getting chopped up, your viscosity drops. All of this is to say a 10W30 will offer better shear stability than a 0W30 at operating temperatures because you don't have to worry as much about the viscosity rating dropping from those viscosity modifiers getting chopped up. Now that said, for most oil drain intervals, this doesn't really come into play. But it's worth noting as a potential downside for decreasing the first number. Okay, but second, what about what GM is doing, going from a 0W20 to a 0W40? Well, as we already mentioned, if you already have hydrodynamic separation in your bearings, using a thicker oil does nothing for your reliability during this kind of engine operation. All you're doing is increasing friction and thus heat, reducing performance and efficiency with no benefit. In GM's case, it sounds like due to manufacturing defects, they needed to push the operating region of the engine to the right to minimize wear, so the higher oil viscosity makes sense. But here's what's really interesting. For the vehicles getting the engine replaced with a brand new engine, they're still recommending 0W20 oil. In other words, if the engine is manufactured correctly, they believe it can reliably use 0W20 oil. If they thought it was going to fail with 0W20 oil, why would they continue to recommend it for the new engines? Now you might say, Jason, they have to recommend 0W20 because of modern CAFE standards. I'm pretty confident this is nonsense, and I'll explain why. First of all, the main thing that almost any company actually cares about is money. The penalty established by NHTSA is $15 per 0.1 mpg per vehicle that falls short of the targeted CAFE standard. Alright, so say going from a 0W20 to a 0W40 gives it a generous 2% decrease in fuel economy. So let's say our vehicle with the 6.2 liter V8 is giving us 20 miles per gallon. 20 miles per gallon, we take a 2% drop in fuel economy, that's 19.6 miles per gallon, or a 0.4 mpg drop, translating to a fine of an additional $60 per vehicle. If GM was confident that replacing these engines and running 0W20 in the new engines was going to cause them to fail, would they rather just pay $60 per vehicle and run them with 0W40, or would they rather run them at 0W20 knowing that they were going to fail and then they have to pay thousands of dollars for every single engine replacement on all of these vehicles? It is a very simple financial choice. If they weren't confident the new engines would last with 0W20, it makes absolutely no sense to recommend it. So if oil was the problem, switching oils would be the solution. Oil wasn't the problem, the manufacturing was. This is why they've corrected the manufacturing process and are calling for the same oil with the new engines. It's worth mentioning, if your vehicle's engine passes inspection and thus switches from a 0W20 to a 0W40 oil, GM will also be extending your warranty to 10 years, 150,000 miles, helping ease concerns of this just being a band-aid fix. But I'm still not fully satisfied, which leads us to our final question. Can using a thicker oil help protect your engine? Yeah, maybe, but I looked at a ton of studies and ultimately you can find whatever answer you're looking for. If you want a study that shows wear increases with lower viscosity oils, that study exists. If you want a study that shows decreasing viscosity doesn't impact wear, that study exists. And to my surprise, there are even studies showing that decreasing your viscosity doesn't result in any fuel economy benefits, in which case, what's the point? However, all of that said, here's why I personally think lower viscosity oils, like those used in today's cars, are no big deal, and why to me, the logical choice remains to just simply use what your car maker recommends. First, a study from Honda in 1999 published in SAE. Looking at 0W20 oils, they found that in comparison to a 5W30, they could achieve a fuel economy improvement of 1.5%. Now, rightfully, they were concerned about wear and oil consumption. So they did vehicle testing, and here was their major conclusion. Quote, there were no anti-wear performance or oil consumption problems when using the 0W20 developed oil in an actual engine. This was 25 years ago. Oil technology and engine manufacturing technology, for some, has come so far in the past 25 years. And yet 25 years ago, Honda didn't see any problems using this thinner oil. Okay, fast forward to 2011, another study published by Honda and SAE where they looked at using thinner oils versus 0W20. They found no significant wear due to lower viscosity was observed in sliding parts. Sounds good so far, other than the connecting rod big end bearing. Okay, well, interestingly, that's exactly where GM's engine problem lies. But again, we're talking about thinner oils than 0W20, and the study goes on to say, quote, there was no significant increase in iron or aluminum in the oils due to reduced viscosity. So they weren't seeing significantly more wear metals in the oil by reducing the viscosity. And the study gives off the vibe that going thinner is certainly possible, stating, quote, low viscosity engine oil that can overcome the practical performance concerns was prototyped. Finally, a study published by Toyota in 2020 in SAE looked at 0W8 motor oil. This is the thinnest oil currently used in production cars. Now, the study they published is absolutely fascinating because they acknowledge that going to a really thin oil formula pushes you leftward on the Stribeck curve, especially at lower engine speeds, as we've discussed, which means more metal-on-metal contact. However, with a film-forming additive, they were able to significantly increase the film thickness at low engine speeds, where you'd need it most, without increasing the oil's viscosity. Basically, they push the position on the Stribeck curve to the right using additives in situations where your engine speed is too low and thus your wear is higher. In doing so, they were able to demonstrate that a 0W8 oil can improve fuel economy versus a 0W16 oil, while still easily passing all of the modern standards regarding volatility, cam wear protection, and chain wear protection. They concluded the newly developed 0W8 oil has achieved both high fuel economy and high reliability. So all of that is to say, it can be done right. Modern engines can be just as reliable while running thinner oils, assuming they're designed correctly. Also, think about it from the manufacturer's perspective. If they recommend too thin of an oil and it pushes them too far to the left on the Stribeck curve, then it actually increases not only wear, but also friction, meaning there is no fuel economy benefit, which means there is no incentive for a manufacturer to push an oil viscosity that is way too thin for their engine. Personally, I believe that if you're going to make a change, like going from a 0.20 to a 0.30, you should actually know why, and you should know that it's actually meaningful. If I were to do this with one of my cars experimentally, I'd run it on the standard oil, say 0W20, get an oil analysis done, then run it with 0W30, get another oil analysis, then go back to 20, and then go back to 30, and see if I get more wear metals with one versus the other. But honestly, because I'm pretty lazy, I'm probably just going to keep using whatever the manufacturer recommends. Because the engineers who design the vehicle know a lot more about it than I do, right? Like maybe the cam phasers work best with the oil the manufacturer recommends. Maybe a thicker oil causes the engine to run hotter. I don't know why I'm making a change and what the effects are going to be. It's not necessarily wise to do so. Okay, one final clarifying point, because you might be thinking, yeah, I'm sure it's fine for Toyota to run 0W20 in their small, low-power engines, but this is a 6.2-liter V8 we're talking about. Now that's fair. Chevy's L87 V8 certainly is going to have higher forces involved than, say, Toyota's 2A RFE, an engine design that called for 0W20 15 years ago, and it is notoriously a very reliable engine, powering the likes of the Toyota Camry and the RAV4. But really, you need to look at the cylinder pressures involved. Okay, so Chevy's 6.2-liter V8 is making 420 horsepower and 460 pound-feet of torque. Toyota's 2.5-liter inline-4 is only making 176 horsepower and 172 pound-feet of torque. And it's true that performance engines can benefit from thicker oils. But if you compare Chevy's engine to Toyota's, they have very similar BMAPs. In other words, the average pressures within these cylinders, within these engines, are very similar. The Toyota engine has remained incredibly reliable with these pressures and 0W20 oil. So it's hard to say the oil is why an engine is or isn't reliable, right? Like you could take 4 of the Toyota engine and then you'd have more power, more torque, and more cylinders than the Chevy engine, but because all of the forces within that engine are still low, you can easily get away with that lower viscosity oil. And just as a comparison, the GR Corolla, the vehicle behind me, can have a BMAP as high as 31.1 bar. That's way higher cylinder pressures than the Chevy, and yet it's still running 0W20 oil. And alright, yeah, there's a couple anecdotal examples of this engine blowing up, perhaps tuned, but I haven't seen any meaningful data that suggests that this is an unreliable engine. Actually, quite some time ago, I was talking with Mobil 1 about thinner oils, and I remember them saying something that stuck with me. For most modern engines, wear is not a limiting issue. Okay, so if wear isn't the limiting issue, you can dip down into lower oil viscosities and take advantage of the efficiency benefits. Better fuel economy, more power. So, can running a thicker engine oil improve engine wear? Yes, we've shown how it can, which justifies GM's approach. However, are modern cars able to maintain reliability while using today's thinner oil viscosities? Also yes. Now if you found this video interesting, I have 2 video recommendations. First, Motor Oil Geek has a video on this and it is great. If you haven't seen it, I'd recommend checking it out. I wanted to cover this topic from a bit of a different angle and cover a few different details, but his video is great. Also, if you haven't yet seen my video on thin oils, I chatted with Mobil 1 about a lot of these subjects and have a detailed video based on that discussion. In fact, folks were asking me about this GM recall in the comments of that video, which is what inspired me to make this. So I will include a link to both of those videos. If you have any questions or comments, feel free to leave them below. Thanks for watching.